Hi, we start our course with chapter 1, which is Propositional Calculus, and introductory section 1.1, which is about propositions. So the idea of the whole chapter is that we want to develop a calculation method or mechanism to assess formally the truth value of compound statements. So first let's fix some vocabulary. So a statement is a sentence that could be assessed as being true or false, correct or not correct. So let's see a couple of examples, what might be a sentence or not. So for example, if you say 3 plus 2 equals 4, is that a statement? The answer is yes, because it makes sense to say that this statement is true or false. And on the other hand, if you have a sentence like this, so this is yes, this is statement, yes it is a statement. But if you say like how are you, then this is not, no. Why? Because you are not answering this question with true or false or yes or no. You are answering this with description of the way you feel at that moment. So that's why this is not a statement. And then a compound statement is a statement built from other statements using connectives. And then for today it will be or and not. And then in section 2 we'll expand the definition. So for example, so here's an example. It says these two lines are either parallel or intersecting. So I want to do two things. First one is to see if you would accept this as a statement. And the second one, what is it that makes it a compound statement? And then how is that leading into our propositional formulas? So first, this is a statement because it makes sense to answer this true or false. So generally at this point we have to kind of dissect a little bit the truth value in English, and at this point we need to agree that that really works the way I will kind of present it here, and it's customary accepted. So generally this is a statement, but it is compound because there is this part or that connects two separate statements. What are they? These two lines are parallel, and then sometimes we shorten one of the sentences. That's how language works. Maybe it would be better, or these lines, maybe we would need them. These lines are intersecting. So that would be a different statement. So these are two statements we treat them as simple or basic, like atoms. And this is a simple statement. And then when we have one simple statement and another simple statement and we connect them with or, then we'll say, all right, this is compound statement. So now what happens? Then we make a little algebra and we start building actually propositional formulas that are kind of theoretically addressing the issue of the way we build compound statements and we analyze their truth value. So what is it? We will actually say the following. All right, in order to describe or analyze this compound statement, we'll build propositional formula. So propositional formula is kind of formal or theoretical or programming version of the real-life statement, and that's called propositional formula. So that's abstract description of a specific statement. So on the one side we have specific objects, they are so specific, abstract. Specific, abstract. So here on specific we have a statement. On abstract we have propositional formula. And that's the topic of our section, of the whole chapter actually. And then what, if it's specific statement, if it's simple, usually we assign to them propositional letters. Most often P, Q, R, that part of the alphabet. P, Q, R, and so on. And then, if you connect two simple statements with OR, then we assign the following symbol. And we read it or disjunction. So, this statement, so here is the statement, and then propositional formula corresponding to this is the following one. I use the letter P here to describe the structure. For the other one I will use the letter Q, not the same letter because these are not the same statements, and then I will use OR. So here it is. So I made a propositional formula that mimics the structure of this propositional, of this statement. And what else? So that's how do we build it? Now how do we interpret it? And the interpretation is, or we say it's true value, we say the following. So this is for OR, here is P, here is Q, here is P, here is Q. And then we say here the following. If both statements are true, then their disjunction is, no, what's this? Or, sorry, that became true, false, true, false. So we have true, false, true, false. So if both statements are true, the injunction is true. If first one is true and second one is false, it's still true, because when we say that OR is true, we mean one of them is true, or maybe even both. So false or true will be also true. But if they are both false, then we'll say here what? We'll say here false. So that's the only place where it's false. So generally this little table, this little calculus, that's why I say it's propositional calculus, this little operation tries to formalize the way we use or we interpret the connective OR. And we'll see where will that get us. Besides this one, we have another similar example. It says, next statement, let me see if I have space ahead. Example 2. Lines A and B are not parallel. So you see, we can think of it like a statement that's built out of the basic statement that lines A and B are parallel, and then someone did the negation. So we can say the following. If we think of P interpreting the fact that lines A and B are parallel, then we'll say the following. Our statement is then described as not P. This is negation simple, so this is, we read it, not P. And what is the table describing how we calculate the truth value? So here it is for negation. So if we take true, if we take false, then negation is doing what? Negation of true will be false, negation of false will be true. So again, this is actually the way to formalize negation of the statement using propositional formulas. All right, and then besides this, here is example 3. Just something, it doesn't have to be in mathematical language. Today is Monday, and today is the first day of the semester. Day of the semester. So what's that? This is again compound statement. And then here is the key connector. So here is and then you see there are 2 simple statements. Today is Monday, I will call that P. And today is the first day of the semester, it is Q. And then the whole structure has corresponding propositional formula, P and Q. Here is the and symbol conjunction. And the table for the conjunction, I'll just try to squeeze it in here so that we have everything on the same board. So here is the conjunction. So here is true, false, true, false. Conjunction, and I ask you, as I said, I cannot prove this. I have just to ask you if you would agree with that. When we say and, we always mean that both things are fulfilled. So that means if you want that statement to be true, the only way to make it true is if both of them individually are true. In all the other cases, you will just get false. So here's the table. So let me summarize our first board. So we analyzed how compound statements are made out of simpler statements. Being simple is just your perspective. So something might be very, very complicated and you call it simple because in that moment you are analyzing how more complicated compound statement depends by its truth value on the simpler ones. But so we generally analyze the situations where compound statement is built out of the simple ones using connectives or and not. To represent them, we used 3 symbols. Here they are. Here is disjunction, here is conjunction, and here is negation. And then we have little tables actually just recording precisely what we basically use in ordinary life to interpret those 2 symbols. One thing where you might disagree, or just you saw that differently, very often when people hear or, either or, like it's here, where was it, either parallel or intersecting, people very often hear that as alternative, so one or the other but not the both. That part is called exclusive or. So exclusive or, we'll rarely use it in our course, but just so that you don't mix it up. Exclusive or is the symbol, like usually people write it with plus in the circle, and that exclusive or then has a different table. That one would be exclusive or true, false, true, false. It's true when they are what? When first one is true and second one is not, or first one. So just one of them, and then it's false here. So if both of them are true, so that's different from our standard or in this part. In this part, our standard or is true, exclusive or is false, because it tolerates only the case when exactly one of them is true. And as I said, in our mathematical language, we'll most often use or. If we do sometimes exclusive or, we'll very precisely emphasize that. And generally, when we summarize all this, I gave in our lecture notes a few examples of situations where you need to interpret or as being standard or exclusive or, and that's very simple to conclude, although I also admitted in the text that sometimes it is really, our language is too ambiguous, so that it's not always easy to recognize how to interpret it. In mathematics, it's a much cleaner situation. All right, so now when we saw how these propositional symbols actually help us to record the process, let's see what happens if we have more complicated statements and more complicated propositional formulas. So basically, how do we build the structure of propositional formulas? A little more complicated. So structure of propositional formulas. Of propositional formulas. Again, I'm not going to go into too formally. You can read more formal approach to this in our notes. I'll just give you an example of some propositional formulas. So for example, if you say something like this, P and Q or not R. So this is a propositional formula. It just encodes basically a little more complicated statement. So basically, how do you recognize this? The best way to actually argue that something is propositional formula is actually to draw its tree. We'll do trees at the end of our course, but it's never too early to use that beautiful mathematical structure. So generally what you want to say here, and if you want to understand what's happening here, the best thing is to do the following. Start with your letters, P, Q, and R. Propositional letters, P, Q, and R, and follow really the story, what was happening. So someone first took P and Q and connected them with and. So here it is, and I put a simple and. So what I have here is P and Q with a parenthesis. And then I will connect that with a symbol or, but my second part is not ready. It's not R, it's not R. So I'll go like this, I'll go with R. I put a negation because it's unary symbols, unary operation. It takes just one R and it doesn't branch or does not connect. It just here is my not R, and now this junction will go between this. So here is not R, here is P and Q, and then here is P and Q, or not R. So generally, this is kind of, this follows the structure and also argues that this is really a formula. So in the definition that you can find in the notes, it basically says the following. What is the formula? So formulas on line 1 is like a recursive definition. So we have letters are formulas. So each letter itself is a formula. And then what if phi and psi are formulas? Then phi and psi, phi or psi, not phi is also formula, are formulas. And number 3, less formally says, that's it, nothing else. Basically, the way I wrote this definition, it would be wrong. Why? Because you are not ready for next step. In that definition, even if you would write a program, you would end up lacking parentheses, and that would give ambiguities to formula. So generally you have to say, and put parentheses around it. Or C. And then not phi, also put the parentheses so that system knows how to do the reading. And that's it. So for example, if you say, is this the formula what I gave you? Basically it's not, because I argue P and Q, here get parentheses, this one gets parentheses, then it should parentheses here and should parentheses here. So this would be formula according to this definition, and otherwise some system would claim that it's wrong. But generally what we do, as we do in just standard mathematics, we try to avoid parentheses as much as possible without losing the meaning. So generally what we say, outside parentheses, when you are done, feel free to erase them. And what else? We do the priorities, and here's priority. Negation has first priority. So if there are no parentheses, you always execute negation first. And then what else? And or have the same priority. Same priority. So you see here, I didn't put parentheses around negation of R because it has a priority. But here I had to put parentheses because without parentheses, system wouldn't know to take Q or negation or R first, would give priority to and or to or. So be careful about that, like plus and times in algebra. So it's very important to keep that in mind. As I said, negation does have priority. All right, and now what? If we have the structure, now since we have precise definition of propositional formulas, now we can talk precisely about the way to decide about the truth value of a formula. So here's an example. This is from the notes, 115. I want the truth value of P or Q, and let's see that better, negation of P and not Q. So what is this? This is a propositional formula. One can write a tree for this formula. And then, in order to discuss the truth value of this more complicated formula, we usually make a table. And making a table, this is very important procedure because that's one of our main strategies for the whole chapter. So make it sure that you can write the table correctly. Basically, it might even help me. If it confuses you, you can skip this part, but it might be helpful. Actually, 3 tells you what are the formulas that you need in building all this. So let me draw the 3. You don't have to, I'll never ask you to draw a 3, but it might help you in building to give you the plan. So here is P or Q, here is negation of Q, here is and, here is another negation, and finally there is that final end. So here's your formula. So basically you make a table where you put all the nodes from your tree. I better start early and tinier. So you start with P and Q. And then every node actually must have its column because you will need to calculate it along the way. So here is P or Q, this node. Then I need not Q, I better save space. Not Q, this is this node. This is P and not Q. I have this guy, now I need negation of that guy. And finally, I have my formula F. I'm lazy to write all this. And then what do you do? We consider all the possible valuations of the letters. So we want to see how this formula depends on the truth value of P and Q. No one can tell you what P and Q are, so you want to analyze all the possible cases for P and Q. Since there are 2 letters, you have 4 lines. Why? 2 letters, that's 2 to the square, which is 4 options. What are the options? So P and Q could be both true. It could be true and false. And then it could be what? False and true, and then false here are the 4 lines. And then what do? You go down the tree calculating each of them. So P or Q, the only case when it's false is here, all the other are true. By the way, it's good to have maybe use here papers with line papers to help you to keep track of the lines. So this is negation of Q, here's your Q, so you invert it, this becomes false, this becomes true, this becomes false, this becomes true. This is PM not Q, so you take P, you take not Q, and take end. So this line and this line end. True and false is false, true and true is true, false and false is false, false and true is false. Now negation of the previous line, so that means just invert everybody. And at the end, what I just got, a line P or Q, I do end between them. 2 and 2 is T, T and false is false, T and T is true, and false and true is false. Do I have that in mind? Yes. All right, that's it. So what did we accomplish here? We said the following. Now we know how the truth value of this compound statement depends on its components. So we can say, all right, if P and Q are both true, statement is true. If they are true, false, it's false. False, true, it's true. And false, false is false. So generally what? You can see basically. Now, what can we conclude, basically? Look, that's extra. So this is just something that maybe you can notice. Where did we get through? We got through in the cases where Q was true. Look at this. When Q was true, formula was true. And when Q was false, our formula was false. When two formulas have the same value for each valuation, we say that they are equivalent. So what we just notice, we say the following: pure Q and negation of P and not Q is equivalent with Q itself. So basically, like in mathematics, like you remember when you have like x plus x equals 2x in algebra, and then whenever you see x plus x, you are allowed to trade it for 2x. In logic, basically, whenever two formulas are equivalent, that means that they are tradable for each other. In every reasoning, this has the same meaning as this. Why? Because for each of these 4 valuations, these two guys have the same value, so they are equivalent. So the same way as we memorize identities among the numbers or expressions, we also memorize identities, logic identities, or we call that equivalences between the propositional formulas. So here is one example of the famous equivalence between two formulas, and it's so often used, and we will use it very often in our course, and it's called De Morgan's Law. De Morgan's Law. There are two versions of it. So it says the following: if you take negation of P or Q, that's equivalent to not P and not Q. And as I said, it's worth memorizing this. As I said, it's used very often in logic, among the sets and everything. You can think of it the following: inside parentheses, you have or. Now negation is outside. If negation wants to attack individually, it's okay. So now negation gets attached to each of them individually, but what happens? Or switches to and. By the way, there is the analogous version of De Morgan's Law, where you attack and get or. By the way, all these formulas have full duality between conjunction and injunction. It's not like plus and times. They don't have full duality. In algebra, these guys do have the full. Whenever you have equivalence with and, you can just rewrite and then and or you can flip and then or there's full symmetry and get another valid identity. Let's practice this just quickly. So what do we do here? So here is P, here is Q. We need both negations individually. Then we need what? We need P or Q. We need negation of P or Q, which is our left side, and not P, and then not Q, which is our right side. Again, we go true, 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 false, false, true, false, false. By the way, you will see in the homework some formulas with 3 letters, then they have 8 lines. I better do that regression. If you have P, Q, and R, then evaluations go like this without specific example. There are 8 lines. How do you write them? I usually like to do it in so-called lexicographic ordering. The simplest way is like this. 4 3, 4 T's, 4 F's. Then here you go 2 2 2. Twice T, twice F, twice T, twice F. And now you alternate each of them. True, false, true. This one alternates on every 2 lines. And you can easily prove that with little combinatoric that we'll study later, that this will really cover, that there is no overlap, and all 8 of them will be covered. So once again, there are 4 of those. 4 T's, 4 F's. Now I get 2 2 2. 2 2 2 2. And now 1 1. You alternate immediately. So if you write it like this, you are sure that you will cover all the possible valuations and none of them will be repeated. Things are a little simpler here. What do? We switch P, so F's in the beginning, trues later on. Now you go FT, FT, P or Q is always true except on the last line. Negation of P or Q is always false except on the last line. Not P and not Q is false here, false here, false here, true here. Look at these 2 guys. FF, 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 TT. For every evaluation they have the same value and they are equivalent. And as I said, this is important for logical reasoning, and we'll talk about it more next week. You'll see examples. Why is that worth checking and worth memorizing? So I gave you actually one example there. Example 119. They say what? Write negation of -2 less than x less than or equals 7. So what? What we want here is negation. What is the meaning of this chain of inequality? That means that x is actually greater than -2 and x is less than or equals 7. So I broke this into conjunction. Chain of inequality is always conjunction. Now, since I want to go separately, I will attack each of them. Negation of x greater than -2. Here I get or, according to De Morgan, negation of x less than or equals 7. This is not 7, this is negation. Like this. And what? What is negation of that x is greater than -2? So here is -2. If you are not greater, you are equal or less. So this is x less than or equal to -2, or x is greater than 7. Here it is. So in order to do this correctly, we really need it in the middle, De Morgan's law, and that shows the value of this law. And then at the end of the section, I'm not going to put them on the board. I'll just comment a few of them. There is a list of some equivalences here in my notes. So here is the list of equivalences. And by the way, there are two columns, because a right column is always dual column of the left one. If you switch end and or, left one becomes the right one. And what are those? Some of them you will recognize. First one is just commutative law. So conjunction is commutative. Second one says conjunction is associative, the same as for the injunction. Third one is distributive law. But interestingly enough, in contrast to the algebra, distributive law in algebra works only when times is outside and plus inside. Here it works both ways, and outside or inside, or the other way around, as you can see it. And then we'll have a couple of famous ones. So for, those are not in algebra. On line number 4 you see P or not P, and negation of P and not P. What is this? These are not equivalences. Those are formulas called tautologies. Those are formulas that are always true. This one is called principal exclusion of the third. It says what? Statement is either true or false. There's no third case. Although some people made lots of discussion about this principle. Is it shouldn't it be used in logic? Something called intuitionistic propositional calculus. What is this? This P and not P just says that there's a principle of contradiction. Contradiction cannot happen. So you cannot have it. So it says it cannot be that the statement is true at the same time as its negation. Then you can see De Morgan's laws, a double negation principle at the end. So negation of not P is equivalent to P. Philosophically, you might agree or not, but when you make a table, it's now there's no more discussion. Once we set the tables and with algebra, you just calculate it and confirm something. And then the one that might be a little surprising, that line next to the last one, is called Peirce's law. It says the following: if you have P and P or Q, you don't need to distribute, that's just equivalent with P. So what's there? And outside or inside, one of the letters was twice repeated. That double repeated one is actually the result. The same way, if you have or outside and inside, then it would be again P. Of course, if Q was twice repeated, nothing special about the letter, then it would be Q, of course. So whenever one of them is twice repeated, or an end when they are appearing, that's called Peirce's law. That's what we had for today. So let me summarize it. The most important thing was, what is it all about? So we want to formalize our way we assign truth value to statements. And in order to formalize it, we needed to kind of code, in a way, simple statements as propositional letters, and then connectives as our logical propositional connectives and or negation. Then to make precise syntactic rules, how do we build the formula, and then how do we calculate the value of the formula for a given valuation, so-called assignment of the value to propositional letters. And then it's important to kind of remember that list of the tautologies or equivalences among the formulas for our future use. And just since this is the first section, let me mention just how our course is organized. At the end of this section, you have a list of problems, and all those problems are your homework. So you will try between now and Wednesday. Let's say I usually think of our class happening Monday and Wednesday. Between now and Wednesday to do all the problems, and that's your assignment. I will collect homework from time to time. By the way, as your extended reading, I also suggested that you might use, you don't have to, you might use Ebb's book if you need more information, more examples. And I will also post on Canvas, I will post one homework list from there if you want to use it. That's not your homework assigned. The only assigned homework are problems at the end of this section in our lecture notes.